Hello, I'm Keegan Williams, and this is my Physics 22 in lab on black holes. So to first understand this lab, we have to know some fundamental physics principles, including the momentum principle, which states that an object's momentum will change over time when a net force is present. And this can be rearranged to get the position update and velocity update equations, which will be used later in the experiment. The gravitational force equation measures the force between two objects using their mass, distance apart, and the universal constant g. The perpendicular and parallel force equations indicate how the direction and magnitude of a force changes, respectively. And below you can see all these equations. So the purpose of this lab is to use a GlowScript model to understand the gravitational forces that govern the movement of celestial bodies that we cannot measure in a lab setting. By analyzing the parallel and perpendicular components of a given object's trajectory, we can determine how its velocity and position change over time. Through this lab, we will see that our models do an effective job of modeling how celestial bodies interact in a system, and how the parallel and perpendicular force components come together to determine the motion of an object in space. In some circumstances, we can see how given certain conditions we can launch an object, such as a spacecraft, into an elliptical orbit. So the free body diagram in the system for this experiment would be the black hole and the star. For part 2, this would be the black hole, planet, and the spaceship. Everything that is not considered these objects is the surroundings. In all three systems, the individual forces on each object is non-zero, but the net force in the system is 0. So for part 1, our seed was my email, the star mass, which I set equal to the sun's mass, delta t, which is a rough amount of time taken to complete one orbit, g, which is universal gravitational constant, which we can use to find the force between two objects, and for the purpose of this experiment, t will be equal to 0 to signify when we first start observing a star's motion. So to calculate the black hole mass, we first had to find the initial and final momentum, and then we calculated the change in momentum and velocity, the change in momentum over time at Fnet, calculating the parallel and perpendicular forces, calculating the mass of the black hole, and the aeroscaling for the GlowScript results. So for part 1, we found that the black hole's mass was 1.98 times 10 to the 34 kilograms, and to the left you can see our Fnet parallel and perpendicular. So for part 2, our initial conditions included the black hole mass, the ship and planet mass, which were constants, and for this time around we set our delta t to 1 second and our initial time to 0. And we also had to find the planet speed, which is determined by rewriting the gravitational force equation to solve for velocity. So additional code needed was the forces acting on the planet and the forces acting on the spaceship. And so to determine the net force acting on a given object, we had to add the two forces exerted on said object and add to compute the net force. And for the change in velocity and position, we used the rearranged momentum principle to determine the new position and velocity after a time t. So for part 2, to achieve this trajectory, I set the initial speed of the spaceship as 5 times 10 to the 7, sorry, that's negative, and 5 times 10 to the 6 meters per second, and this ensured that I did not collide with the black hole or the planet. With this initial velocity, the spaceship's trajectory was altered enough to slingshot right around the black hole. The effect of the black hole on the net force of the spaceship is most apparent when the spaceship is closest, and this is because the force of the black hole on the spaceship is inversely proportional to the square of the distance, so the total net force on the spaceship will be greatest during this interval. So in both parts of the lab, we observed that the gravitational force decreased as a given object moved away from all the other objects in the system. This is due to how the parallel force decreases as the magnitude of momentum decreases. Since the spaceship and stars always go in a circle, the perpendicular force will always be changing. In both experiments, the greatest force was when a given object was closest to another object in the model. In part 1, the net force on the star in the model was simply towards the center, whereas the net force on the starship in part 2 was the sum of the net forces in regards to the black hole on the planet. So possible sources of error in this lab include rounding errors that resulted from using a value of g as two significant figures. Using a value with more may have yielded results that were more accurate. Additionally, averaging the values of the black hole may have yielded slight inaccuracies if significant figures were dropped during the calculation. So over the course of the iteration, our results for net force in regards to the black hole mass may have become increasingly inaccurate. So how does the net force and its parallel perpendicular components differ from the rate of change in momentum and its parallel and perpendicular components? The net force is the rate of change of momentum over time, whereas the rate of change of momentum does not depend on time. So this indicates that these values have different units. This indicates that the parallel component of net force changes the magnitude of the force, whereas the parallel component of the rate of change of the momentum changes the magnitude of the velocity. Similarly, the perpendicular component of the net force changes in the direction of the net force, and the perpendicular component of the rate of change of momentum changes in the direction of the velocity. So if we wanted to enter an orbit around the black hole, such that we did not crash or escape the pull of gravity, we can find a certain initial velocity using trial and error, and to achieve this, I found one as negative 4 times 10 to the 6 and 1.15 times 10 to the 7. and this smaller velocity and the negative x allowed the spaceship to not overshoot the black hole and escape the pull of gravity. So through trial and error process, I had to ensure that the y velocity was high enough such that it could escape the gravitational force exerted by the planet and stay in range of the black hole's gravitational force. So in closing, we gained a deeper understanding of the gravitational force equation and how to apply it in scenarios where running a realistic experiment is not feasible. By modeling the starship with the black hole, star planet, and black hole systems, we successfully analyzed and observed the changes in parallel and perpendicular forces over time.